So many of you may have heard of Toeplitz matrices. These have been studied for quite some time. They're just matrices that have constant values on the diagonals. They can be finite or infinite, and you can study their spectrum. You can try to diagonalize them if they're self-adjoint. Let me see if I can adjust this to the size of the. Now this should be. Yes. And where do these matrices come from? Well, they come from this sort of trick, which is interesting. You first need a space of functions on some measure space. You can multiply by bounded functions on the space of L2 functions, and this will give you a bounded operator, and then you can compress that multiplication operator, which is a very boring sort of quantization that doesn't do anything, onto some closed subspace. So you can consider L2 of the torus, yes, and this has the orthonormal basis of these elementary harmonics, and we can just consider this for each bounded function on the circle as one. We can consider the operator of multiplication by f. Right? This gives us a bounded operator. This is technically, you can think of this as a completely trivial quantization. Right? But now if we compress onto, say, the subspace, here I'm going to consider the subspace spanned by the harmonics E0 through En. This now allows me to define an operator from Hn to Hn, which is a finite dimensional space. So now I get a matrix. And yes, so what I do is I take the multiplication operator, I restrict it to Hn, I apply it. Now the multiplication operator will give me something in L2 of the torus, maybe not in Hn, but then I project it down to Hn, and I now have a map from Hn to Hn. So it's not difficult. It's just an elementary calculation to see that, in fact, the matrix coefficients of this matrix, right, with respect to this orthonormal basis, are constant on diagonals. And so we get a Toeplitz matrix. Maybe without going into why I'm arguing that this is a sort of quantization, which I'll get into in just a second, one of the first things that you notice is that this is a linear map. So this operator T depends linearly on F. Okay. In fact, this operator, this Toeplitz operator in this case makes sense not only for bounded functions F, but for any L1 function on the torus. So it is linear because it depends linearly in F. Yes. My inner products are always linear in the first variable and antilinear in the second. And unfortunately, it's cut off the. Here I've rewritten this as an inner product of F with A, E, K minus J, which is a complex conjugate of E, J minus K. So you can just write out explicitly the entries of this matrix. But the point is that the operator T sub F depends linearly on the function F. It's a matrix now that these operators do not commute with each other anymore. And this is called the Toeplitz operator with symbol F. So F is called the symbol of the operator. And the Toeplitz operator with symbol F conjugate is the adjoint of the Toeplitz operator with symbol F. So if you have a real valued function, you get a self-adjoint operator. So this is not enough to justify calling it a quantization, but it's a good start. In fact, this is a theorem that goes back to before the, I guess there was technically the old quantum theory already in 1915, but this goes before the modern theory of quantum mechanics. This beautiful result of Sago in 1915, if you consider some L1 function on the circle, and we'll suppose that it's real valued, and that guarantees that all of these Toeplitz matrices that I mentioned are self-adjoint, and so they're diagonalizable. They have then real valued eigenvalues. And this function, I'm going to choose a real number because f only takes real values, such that the level set of f at a has measure 0. Then there's a sense in which when I let the dimension n go to infinity of these subspaces h sub n that I'm compressing these operators onto, the distribution of eigenvalues sort of recovers the behavior of the function f. So if I take the limit of the proportion of eigenvalues of the matrix, this is the number of eigenvalues of this matrix TFN that are greater than a. If I take the proportion of them that are greater than a and take the limit as n goes to infinity, I just get the measure of f inverse of a to infinity. It's a very beautiful result. Okay, so I'm really not so interested in this talk in this type of Toeplitz operator on, say, subspaces of L2 of the circle. By the way, we could consider the full Hardy space on L2 of the circle, and then we would have infinite Toeplitz matrices. I'm more interested in the way we constructed these matrices. More than being constant on the diagonal, I'm more interested in this general idea of multiply and then project. Okay, and in fact, maybe I don't know how. I don't know. Maybe this is all of you know this. But what I'm going to convince you now is that Weyl quantization is an example of Toeplitz operators, basically, in the case of the Fock space. So you can consider Toeplitz operators whenever you have something like an L2 space of functions on a measure space, and then you have some closed subspace of that L2 space. In fact, you can go a little bit more general because we could consider rather L2 sections of a line bundle or a vector bundle over a space, and then some closed subspace. I can consider the orthogonal projection onto the subspace H, and then I just, for each bounded function on L infinity of x, I'm choosing f to be a bounded function because I know that this will work and it will give me a bounded operator. Of course, in some sense, we really care about the unbounded operators, but we study them using bounded operators. So we're going to start here. Consider an L infinity function. The Toeplitz operator with symbol f is just going to be the compression of the multiplication operator onto this subspace. And just as before, this is linear. It goes from L infinity to the space of bounded operators on the Hilbert space H. Unfortunately, it's cutting off the bottom here. So it preserves a star operation. So what I mean by that is that the Toeplitz operator with symbol f conjugate is always the adjoint of the Toeplitz operator with symbol f. So real valued functions give you self-adjoint operators. And the operator norm of T sub f is always less than or equal to the L infinity norm of f. This is, in fact, an operator of norm less than or equal to 1, always. Okay. Now, this is not enough to really convince you that this is that quantization is a good name, other than just vague analogies, right? It's sending functions to operators and real valued functions to self-adjoint operators. But to really convince you, I'm going to consider first this example. We can consider Cn with this Gaussian measure. So this is the bosonic Fock space, but seen as a space of holomorphic functions with respect to the Gaussian measure, right? So I'm sometimes going to write it as f of Cn and sometimes f sub n, but I'm just taking the L2 space of Cn with the Gaussian measure, and I take the intersection with the holomorphic functions. This is really the same as the bosonic Fock space on Cn, because you can think of the monomials as just being sort of symmetric tensors, right? Because the monomials in the entries in Cn all commute with each other. In fact, these are the sort of normalized, the monomials are all orthogonal to each other. You just need to normalize them to get an orthonormal basis. This space famously has a reproducing kernel. It's very easy to write down. And that means that for each point in Cn, there's a function k sub z, so that if you take the inner product of your function f in the Fock space, with k sub z, it magically gives you the value of f at that point. So apologize here. This is f of z equal to the inner product of f with kz. And this is an integral of f of w times kz of w conjugate. And so the integral kernel here is what I'm going to write as capital K. And that's why k sub z of w is k of w z. Right? That's why the order switches, because I have the complex conjugate here, integral. And this is a function that is holomorphic in the first variable and anti-holomorphic in the second variable. You can think of it as being holomorphic on Cn times Cn bar, where Cn bar is the same as Cn, but it has the opposite holomorphic structure. So you can consider the Heisenberg group. In some sense, we should really be thinking of just the group Cn or R2n. But that way, you would need to consider projective representations instead of unitary representations. And this has this very well known, this is equivalent to the Schrodinger representation because it has to be. This representation of the Heisenberg group on the Fock space. It's an irreducible unitary representation. I've fixed Planck's constant to be 1 here, basically. And not just the Heisenberg group. In fact, the full Galilean motion group acts. So this is a spin 0 representation of the Galilean motion group. So there's also rotations act here. And that's easy to see because this Gaussian measure is invariant under rotations. Okay, so now for every bounded function on Cn, Cn now you can think of as phase space, right? Rn plus I times Rn. So the real part you can think of as position, and the imaginary part as being momentum, if you like. And so you would want to associate an operator, a bounded operator, to each bounded function, and more generally to at least a nice class of certain real-valued unbounded operators you'd like self-adjoint operators on Fn on this side. But at least for the bounded functions, what we can do is just take the function f and construct the Toeplitz operator with symbol f. Just press, like I said before, using the orthogonal projection. And this is really Weil quantization in disguise. So there's 2 things called restriction maps that are closely related that I'm going to show you guys. And this works in this case of the Fock space, but it also works in many other cases of homogeneous spaces, such as the bounded symmetric domains, and also in the case of flag manifolds, which is, in theory, the main subject of this talk. So let's consider the following map that goes from the Fock space onto the regular L2 of Rn with Lebesgue measure. So Lebesgue measure is invariant under the action of Cn by translation. I'm sorry, under the action of, Rn by translation, under the action of rotations, orthogonal rotations, right? So the Euclidean motion group preserves the measure on Rn. It does not preserve the measure of the Gaussian measure, but I'm not using a Gaussian measure. Okay. So I'm going to define this map called R for restriction, because that's basically what I'm going to do. I'm going to take these holomorphic functions and restrict them down to the real line, well, to Rn. Right? But I'm going to multiply by this Gaussian function, okay? And I'm doing that in such a way that, so I'm not just restricting, I'm also multiplying by this Gaussian. Sorry, this is the normalizing constant that when I first started writing this out, I forgot to write in there. This operator R, then, this here is what allows me to go from holomorphic functions that are L2 with respect to the Gaussian measure to L2 functions with respect to Lebesgue measure. Right? Obviously, this map cannot possibly be completely surjective, because whatever you get when you restrict a holomorphic function to Rn, it has to be real analytic. Nevertheless, it'll be dense, because in fact, it's going to contain the Gaussian times all polynomials, because all polynomials in Z are in the Fock space, and they restrict down to polynomials x to the n. So we have all polynomials in x times Gaussians, and so the image is dense. But it's also injective, because a holomorphic function is completely determined by its restriction to Rn. And this operator R intertwines the action of the Heisenberg group on Fn with the Schrodinger representation on L2 of Rn. In fact, it intertwines the full representations of the Galilean motion group. Okay? And once you have an intertwining operator in representation theory, this is very powerful, because what you can then do is take the polar decomposition, and the individual parts of the polar decomposition also have to be intertwining operators. In fact, there's a unitary part. This is unitary, not just a partial isometry, because I said R has a dense image and it's injective. So this is a unitary, this is an intertwining operator that gets you from the representation we defined on the Fock space to the usual way of realizing the Schrodinger representation on L2 of Rn. When you do this, then, you can consider, these are, I'm being a little bit fast and loose, but you can sort of, you can define the Toeplitz operator with this unbounded symbol. This is the function that sends z to the coordinate zk. Okay? And this is the function that sends z to the conjugate of the kth entry of z and cn. So when you sort of take the sandwich of the Toeplitz operator with this intertwining operator, you get precisely position qk plus I times momentum, the kth entry of momentum. Same thing, if you take the complex conjugate of zk, you get the corresponding one here. If you take a real part of zk, you get just position. Imaginary part of zk, you get momentum. Okay, so this is literally giving you the position and momentum operators. And it's easy to see that also t with symbol z sub k to the m is going to be the nth power of this. And also here, the nth power of zk bar is going to be the nth power of this. This really is Weyl quantization. But just a little bit more about what's going on here. Now, if you take any bounded operator on the Fock space, this operator S now has an integral kernel. In fact, the integral kernel is going to be holomorphic in the first variable and anti-holomorphic in the second. And what you can just do is take the inner product of S applied to k sub z with k sub w, right? So the this gives you a sort of a nice sort of continuous version of matrix coefficients with respect to, I guess physicists would call these coherent states. Now, the nice thing that's going on here is that, and it's easy to prove. You just use the S psi for uni psi in the Fock space. Evaluated in Z is just S psi inner product kz. But then S can be moved over to this side to give you S star, which then has to be the integral, because it's the inner product is given by the L2 inner product, psi times the complex conjugate of this, which is the complex conjugate of S star kz inner product kw. And then this gives us exactly what we wanted. This is the integral kernel for S. Okay, so now if I take two functions in the Fock space and I want the matrix coefficient TF psi applied to phi, it's easy to see that this is just the matrix coefficient of the multiplication operator with respect to those functions also. Because I'm sort of applying on both sides the projection, but the projection does nothing to psi and it does nothing to phi. So then the integral kernel of the Toeplitz operator is just whatever the inner product of f times kz with inner product of kw is. Okay, and it's easy to see that also another nice thing is that the Toeplitz operator with okay, so this is dimension 1. So this is n equal to 1. The Toeplitz operator with symbol z to the k applied to z to the m is just a multiplication operator, because it's also holomorphic. You multiply by a holomorphic function and project to the holomorphic functions, you are not doing anything. And when you normalize things, so p sub k, these are the normalized monomials. Well, you get just the standard raising and lowering operators when you look at the Toeplitz operator with symbol z and z bar. Okay, but there's something else that's going on here that I want to point to. And that is, if you take an L2 function on Cn, then the Toeplitz operator with symbol f, now f is no longer required to be bounded, but the Toeplitz operator with symbol f will be a Hilbert-Schmidt operator. So even better than bounded. In fact, you can let f be a compactly supported distribution, which is very singular in some sense, and you always get a compact operator. Now, what that means is that the integral kernel now has to be an L2 of Cn cross Cn with respect to the product of the measures. And in fact, you can write the tensor product of the Fock space with its dual as precisely another Fock space, right? But now with Cn times the opposite complex structure over Cn, right? When you do this, this is just the standard identification of Hilbert-Schmidt operators with their integral kernels. And this is unitary. And this also intertwines nicely the representations. You can define pi defines a representation on the Hilbert-Schmidt operators, a unitary representation, just by acting by conjugation on the operators. And then also we have a nice representation called pi tensor pi bar that acts on this space, which just sends each element G of the Heisenberg group to pi of G tensor pi of G conjugate. And so these are really the same representation, right? Mm-hmm. So this is L2 with respect to Lebesgue measure on Cn, not with respect to the Gaussian measure. But yes, it will have to give you a Hilbert-Schmidt operator, which is now with the Fox acting on the Fox space where you do have the Gaussian measure. Then you will get the yes. Then it will no longer be L2 because, like I said, this is no longer a finite measure. This is just a Lebesgue measure. Yes, yes. So being L2 on the Cn with respect to Lebesgue measure is a rather strong condition, much stronger than being L2 with respect to the Gaussian measure. And that's what's causing this to happen. So I mean, we can have little singularities, but they can't be too big, and they need to still die out at infinity. But the nice thing, at the end of the day, you don't really. This is not maybe what you want to focus on. But the nice thing is that this is a Hilbert space. So there's a whole lot of nice tools you can use to attack this space of operators. You have a unitary representation, so all of the tools of unitary representation theory applies. And then maybe in the end, you then take what you learned at the end of the day and apply it to some larger class of operators if you can. At least that's how I see it. So we have this operator that unitarily, basically it's the same to consider the integral kernels, which are holomorphic in F and anti-holomorphic, are holomorphic in the first variable, anti-holomorphic in the second, and these are L2 with respect to the Gaussian measure on Cn times Cn. And then on the other hand, we have the Hilbert-Schmidt operators. And here I am talking about things that are L2 with respect to the Gaussian measure. Okay, so with every holomorphic function on Cn times Cn bar, restricting to the diagonal is also injective, just like restricting to Rn. So I define this other restriction operator where I again restrict, and I'm multiplying. By the way, this is really k of 1 over k of z times z, 1 over k of z comma z. That's where this Gaussian is coming from. But once again, this is sending me from this space to L2 of Cn, but now I've built in the Gaussian. I get things that are L2 with respect to Lebesgue measure again. So this is another bounded operator. It's injective, and it has dense range. So again, you can polarize it. Okay, so you can also calculate explicitly R star. R star phi then has to, for each phi in L2 of Cn, has to be one of these sort of holomorphic in the first variable, anti-holomorphic in the second variable L2 functions. And you can explicitly calculate it. Also, it's very easy to see what the reproducing kernel on this space has to be. It's just sort of a integral kernel on the first variables times a complex conjugate of the integral kernel on the second variables. Yes, it's very, very, yes, it is. I would have to think in order to write down exactly the formulas, but it is, yes. That is exactly what is going on. But sort of thinking of these in terms of restricting the diagonals and then polarizing this. When you polarize this, when you get the polar decomposition of R, you obtain what is called the Siegel-Barkman transform, I should say. If you've heard of this before, the both for this restriction operator and the other, the unitary part of the polar decomposition is called the Siegel-Barkman transform. And you can calculate, again, the integral kernel of R star phi, which is an operator now. And its integral kernel is just the integral kernel applying to the Toeplitz operator phi. So this is this operator V applied to T sub phi. So somehow R star is really the Toeplitz quantization. And then, so what is R? This Toeplitz quantization map, it goes from, if it goes from L2 of Cn to this Hilbert to Schmidt operators on B of Fn, should make sense to talk about its adjoint. And it does, and its adjoint is just the famous Berezin transform, where you take, this is basically, you take the integral kernel of the Toeplitz operator with symbol A. Well, I'm sorry, not the Toeplitz operator with symbol A. The integral kernel of the operator A, because every bounded operator now has an integral kernel. You restrict to the diagonal, which is enough to recover the operator, and you divide by kz times inner product kz. So this is k of z comma z. And I've just put in this normalization of the measure, which is optional, really. It's just a matter of where you want the 2 pi to the n's to show up. And so then the T star is usually called B for the Berezin transform or Berezin transform. That goes, in fact, you can define it for bounded operators, and it goes to L infinity of Cn also. It's defined this way. And again, there's uniqueness here. So these operators are uniquely defined by their Berezin transform. And so this operator R was really just BV inverse in disguise, and R star was really just VT. So R star is just BT. BT is also called the Berezin transform. It's the Berezin transform of a Toeplitz operator with a given symbol. So it's sometimes called the Berezin transform of that symbol. The point is that this is then just convolution of a function with this Gaussian, and you can, this is just a Fourier multiplier. You take the Fourier transform, and you know exactly how it acts. So this allows you to sort of explicitly calculate the unitary part of the polar decomposition of R. And I've probably spent way too much time going through this example. And by the way, a nice article where you can see this sort of a way of looking at Weyl quantization at these restriction operators. And they don't use the word Toeplitz operators, but this is all really in there. Is this paper by Bint Ørsted and Ginkai Song from the 90s, which nicely put everything into this sort of language. Am I going the wrong way? Yes. So it's in the references. So at the very last slide, it will be there. And okay, okay, yes. So this same game will work not only for this case of the Fock space on Cn. The Cn has a transitive action of this Galilean motion group. And in fact, there are other homogeneous spaces where you can do this same sort of quantization game, just exactly the same. And the nice thing about that is that when you have a homogeneous space, you can usually calculate things explicitly. You can explicitly calculate the spectrum of the Laplace operator on a symmetric space, for instance. It's very nice and easy formulas. You can, there are Fourier transforms that are defined called the spherical Fourier transform. And so you can do exactly what we just did with the Fock space, and up to and including writing down this function and taking its Fourier transform. The corresponding Fourier transform, spherical Fourier transform, was taken in the 90s by Unterberger and Uppmeyer. Sorry. Yes. So the sort of canonical other example to consider is the unit ball. This is what's called a bounded symmetric domain. It's a bounded domain in Cn and it's a symmetric domain. So if you notice, multiplying by -1 is actually an isometry of this domain with respect to the sort of hyperbolic geometry metric on the unit disk. And the same thing works for the unit ball. So the unit ball Bn is just a space of the set of vectors of absolute value less than 1. Here you have this action of the group SU in 1 by Mobius transformation. And the subgroup that fixes the base point 0 is this compact group, S of UN cross U1, which is isomorphic to UN. Okay, so it acts by Mobius transformations. The measures we want to choose, there's actually a whole family of measures. Just there really is for the Fock space too. I was just leaving the Planck constant out of it, but here I'm writing it back in essentially. There's a normalizing constant, and then this 1 minus absolute value of z squared to this power lambda. And lambda needs to be a value greater than n. So lambda equal to 0, if we were considering that case, would give us the invariant measure. So this unit ball has a measure that's invariant of the action of G. These measures are not invariant, but they're sort of like the Gaussian measure was. These are finite measures on these domains. These are reproducing kernel Hilbert spaces. The reproducing kernel has a nice formula you can write down. And there are these unitary representations that are famous in representation theory because they're called the holomorphic discrete series representations, because they appear discretely in the regular representation of the group SUN, 1. And it may be weird. In fact, when I was first learning about them, it seemed weird to have a continuous family that was called a discrete family. And that's because really these only make sense if we're considering the group SUN1 for integer values of lambda. You need to go up to the universal covering of SUN1 for these representations to be well defined for non-integer values of lambda. And then they sort of discretely appear in the regular representation mod the center. Sort of like, I don't know if you've ever noticed, if you've ever worked with these sort of reduced Heisenberg groups, where you have Cn times a torus instead of Cn times R. And that's enough to make these representations, in fact, be square integrable. What that is, I'll get into in a bit. So these representations are defined by just translating the functions as usual, and you have to multiply by this cocycle, which I've written in as Cz plus d to the lambda, where I put this in quotation marks because when lambda is not an integer, this doesn't really make sense, but you can make it make sense if you go up to the universal covering. Let's see here. Sorry, the slides got a little bit out of order when I scanned them, apparently. You can then do this same quantization game with the Toeplitz operators. It all makes sense. Basically, everything that I wrote previously for the Fock space also holds here. And lambda goes to infinity is a sort of semi-classical limit. So in some sense, these operators convert more and more into something like multiplication by f. In fact, if you take the Bayesian transform of these Toeplitz operators, it converges to f. And there's a sense in which the Lie bracket of the commutator of TF and TG converges in some asymptotic sense as lambda goes to infinity to the Poisson bracket. And the sense, the technical sense is in terms of the Bayesian transform. Yes. No, these are no longer finite rank because they're orthogonal projections onto this. I should have said this. I never mentioned this. I should have said exactly what A2 lambda is. It's again the space of L2 functions with respect to these measures mu lambda that are holomorphic. These are called Bergman spaces in this case. So they're L2 functions and holomorphic. Just like for the Fock space, they're L2 with respect to these finite measures mu lambda that are only finite for lambda big enough. And for lambda equal to 0, you would have gotten the invariant measure, just like with you when you consider the Gaussian measures, you put the parameter Planck's constant to 0, and you would get the Lebesgue measure, right? So so this is the orthogonal projection from the full L2 space on the ball with respect to that measure mu lambda onto the space of holomorphic L2 functions. So there's there was an interesting discovery that was made. This is sort of starting in the late 90s, early 2000s, by several mathematicians here in Mexico, Nikolai Vasilevsky, who sadly passed away very recently, Sergei Grudsky, and my postdoc mentor, Raul Quiroga, that there are several large families of Toeplitz operators that commute. Sort of similar to what you have in the Fock space case, where all of the position observables commute and all of the momentum observables commute. But you can also find similar large commuting families of operators. And they seem to have something to do with functions that are invariant under actions of a group. So in the Fock space, the position, the sort of functions of position are just that. They're functions of position. So they're in sort of constant on the orbits of the momentum part of the translation group, and vice versa for the functions of momentum. Sorry, I bumped myself. So, so for the disk case, there's sort of three cases that are interesting to look at. You have this maximal compact subgroup, which is U of 1, which is just acting by rotation. So all the radial functions on the disk have Toeplitz operators that commute. So all the Toeplitz operators, the symbols equal to a radial function commute. Also the orbits of this SO11, which SO11 has an orbit which is basically the real points of this complex domain. So this is the real ball. This is the open interval from -1 to 1. And every function that's constant on the orbits of this group gives you Toeplitz operators that commute. Same thing here. So for many years, they believed it's had something to do with maximal abelian subgroups, right? Which sort of makes sense if you're thinking about the Heisenberg group in the Fock space. You have these large abelian groups, right? Corresponding to the translations in the momentum and in the position parts of phase space. But it turns out that it really doesn't necessarily have to do with maximal abelian subgroups, but rather, okay, and now yes. It rather has to do with the following. So before I go on to that, I just wanted to mention that there are many other bounded symmetric domains. Instead of just the unit ball, you consider these domains of P by Q matrices that have satisfy Z star Z less than the identity. And then there's sort of generalized Mobius transformations that act. You can write down explicitly the measures and the reproducing kernel for those spaces. And we proved, this is a JFA paper from 2014. What we proved was that if the Toeplitz operators have invariant symbols that are invariant under a subgroup H, where the restriction of this representation pi lambda to H is multiplicity free, then they all commute. And this is essentially a corollary to Schur's lemma. And if H is compact, then we also proved the reverse implication, that if they all commute, then this restriction has to be multiplicity free. So that's the only way it could work. And examples, there's also a nice collection of examples we have where this multiplicity free restriction obtains. For instance, if you take the maximal compact subgroup of one of these G's that coming from the bounded symmetric domains, then pi lambda restricted to the maximal compact is always multiplicity free. So in this case, you would have SUPQ and S of UP cross UQ. And also, if you sort of restrict to the sort of the real points, SOPQ, that also is going to be multiplicity free. There's also a Siegel-Bargmann transform that where you can sort of do the same sort of trick we did restricting from holomorphic functions on C into the real line. You can restrict from holomorphic functions on the domain of P by Q matrices over the complexes to the domain of P by Q matrices over the reals. Okay. And I think I now have very little time for the actual subject of my talk, which I suspected this might happen. I apologize. So this is sort of what people have been doing in this area, and the new results here are from a JFA paper that came out this year, just in May, I believe. But it's been on the archive since last year. Let me just see if I can. Yes. So I think we can skip through all of this. Basically, what we're considering here are domains that are compact, but where the group that is acting, the G, so to speak, in our quotient, in our homogeneous space G mod K is also compact. And we also want them to be holomorphic manifolds, so we can still consider. We're no longer going to be considering holomorphic functions, because holomorphic functions on a compact holomorphic manifold are just constants, but rather holomorphic sections of line bundles, right? And this is famously came up in the history of representation theory because you can construct every irreducible representation of a compact connected Lie group as a space of holomorphic sections of a certain line bundle. So that right there is telling you there should be connection with Toeplitz operators. So precisely what's going on is if you have any compact group for the moment, any compact topological group, then you consider the action of the group by, okay, so this is just the statement, sorry, that says that every every unitary representation of a compact group decomposes uniquely as a direct sum of irreducibles. So we don't have to worry about direct integrals here. And everything in the paper works for all compact connected Lie groups, but I'm just going to consider U of n to simplify the notation so we don't have to talk about roots and weights. So I'm going to consider the group G equal to the unitary group U of n. It has a complexification. The complexification of this group is the group GLNC. The Lie algebra of GLNC is just the Lie algebra of n by n complex matrices. And it's the complexification of the Lie algebra of U of n, right? The Lie algebra of U of n are the the skew adjoint matrices. And it's not difficult to see that the Lie algebra of GLNC is literally the complexification of this real Lie algebra. Okay, and the trick is, okay, so this is just reviewing the fact that there's a relationship between representations of the Lie group and their derivatives that are representations of the Lie algebra. So you can move between them easily. And the same thing, intertwining operators for representations of the group are the same as intertwining operators for the corresponding derived representations of the Lie algebra. As I said, the Lie algebra for GLNC is literally the complexification of the Lie algebra of U of n. And every representation of G complexifies functorially to a complex linear representation of the complexified Lie algebra. Okay, now, what is a flag manifold? So imagine a flag is just take Cn, okay, a vector space of finite dimension, and we'll take some k indices that are increasing from n1 to nk, strictly increasing. And then a flag of this shape is just a series, an increasing chain of subspaces with dimensions equal to these. Okay. So the reason they're called flags is, imagine they have the first part is 0-dimensional, so it's a point. Then you have a 1-dimensional subspace that's kind of like the flagpole, and a 2-dimensional subspace that's kind of like the flag. And that is if this were to be 1, 2, 3, etc. A full flag is exactly a flag of this shape, where you are required to have subspaces of all dimensions. Now, what's interesting is the full group GLNC acts on this space of flags because you can just apply that elements of GLNC to each one of these subspaces, and the dimension doesn't change because they're invertible linear maps. And it turns out that this is a transitive action of GLNC, but the subgroup U of n also acts transitively. Okay, so what that means is that these sort of flag spaces, or also called flag varieties or flag manifolds, are compact, and U of n acts transitively. It turns out that, so if you choose a maximal torus for U of n, usually you want to choose the group of diagonal matrices with entries in S1, then for instance, the full flag manifold of flags of dimensions 1, 2, 3, etc., is just the quotient of U of n with the maximal torus. And now, what is the stabilizer group of some point in this flag? Well, if you consider the action of GLNC, you'll get these. These are called Borel subgroups. There's maximal solvable subgroups of GLNC. We have upper and lower triangular matrices, and they're sort of opposite to each other. So I'm calling them B and B bar. And the intersection with U of n is just the torus T. So the whole point of this is that you can write the flag manifold for the full flags as just U of n modulo T or GLNC mod B bar, because B bar is the isotropy subgroup when you act with all of GLNC. This is a holomorphic manifold because it's a quotient of two complex Lie groups. This is a quotient of compact groups, so it has to be compact as also. Which is maybe not completely obvious when you first look at it, that this should be compact and that this should be holomorphic. But that is the way that you go about constructing. Sorry, I don't have time, so I'm going to move through this. The representations, the irreducible representations of U of n. So there's this famous theorem called the highest weight theorem that says that, in particular for U of n, there's exactly one irreducible unitary representation associated to each of these multi-indices, where lambda 1 through lambda n are now allowed to be any integers, positive or negative, but I am requiring lambda 1 to be greater than or equal to lambda 2, etc. So I can also choose a different basis here. These are called the fundamental weights for reasons I could explain later. But those are just the sum of the first I elements of the standard basis. And each one of these dominant integral weights, they're called, are just some linear combination with non-negative integers of these fundamental weights, except that for the last one, it can be any integer. Okay, and so the point is, how do I construct these representations? And I just need to first construct corresponding characters or one-dimensional representations of the Borel groups, B and B bar, which I do, you can do easily this way. And okay, I'm going to have to move here. Then I will consider, this is an induced representation. So I'm taking this one-dimensional representation chi lambda, and I'm inducing it to a representation of UN. So I consider all L2 functions on the unitary group that satisfy this sort of equivariance condition. This is telling me I have sections of this line bundle, right? But this line bundle is also holomorphic, so I can consider holomorphic sections. And the irreducible representation with highest weight lambda is just the action of the group U of n by translation on the holomorphic sections of this line bundle. And so the full L2 space, I can still decompose it, right? Using something called Frobenius reciprocity. I know that it's sort of going to decompose into a direct sum over all the possible representations. This should be pi in G hat of H pi, and then I just need to take the tensor product with the space of lambda weight vectors in H pi. And the point is this Bergman space, so to speak, of holomorphic sections of this line bundle then carries the irreducible representation with highest weight lambda. We can consider the orthogonal projection, and you can explicitly write what the Bergman kernel is. It's this function called a conical function, and there's explicit formulas in terms of these principal minors of the unitary matrix. So you start with, from the lower right-hand corner for various technical reasons. This is the this sort of reciprocal principal minor coming from the lower right-hand corner, where you take an I by I submatrix and take its determinant if I is between 1 and n minus 1. And then I use the coefficients of the highest weight lambda to raise these different principal minors to different powers. And so you can explicitly write out what this kernel is, just like you could for the other cases. And what's new in our paper is basically we've proved all the standard results you want for Toeplitz operators. What's different here is that this Toeplitz quantization map can no longer have a dense image, because the Bergman space is finite dimensional, and the L2 space is infinite dimensional. So it's no longer injective. However, it is still surjective, because I'm going from the full L2 space on the flag manifold to this finite dimensional space of operators on a finite dimensional vector space. And we've sort of explicitly identified what the kernel of this Toeplitz quantization map is. We've encountered other large families of Toeplitz operators that commute, like analogous to all the position operators that commute and all of the momentum operators that commute in the Fock space case. This is the Barrison transform. It has an integral kernel that's the absolute value squared of this conical function. And we finally proved, we have some formulas that allow you to, at least in principle, calculate the Barrison transform of the Toeplitz operator with a given symbol. These are matrix coefficient functions. And finally, what I wanted to get to, at least before the very end, is we have some semi-classical limits that we can take. Now, what's interesting is we're no longer taking these in just one direction, because these highest weights are sort of linear combinations with non-negative integer coefficients of these fundamental weights. And so you have sort of in different directions in which you can go to infinity. And the only thing we require is that the minimum of these coefficients needs to grow at least as c times log n for all c. And the maximum needs to grow at most polynomially, for some polynomial. These can probably be relaxed a little bit. And when you do that, you get that the integral kernel of the basically this operator RR star that we saw earlier, or BT, is they form an approximate identity. So then these Barrison transforms of the Toeplitz operator symbol F converge to F as n goes to infinity for any of these sequences. And whenever the representations are self-conjugate, then we also have that the product of Toeplitz operators with given functions converges to the product of the symbols. And I think I've already come. One last corollary is that I think I promised something related to tensor products of representations. In fact, one of the corollaries is that decomposing a tensor product of representations is notoriously difficult in general, but we have a nice sort of limit result that says that for n large enough, any given representation pi will appear exactly this many times, where this is the number of vectors that are L invariant, where, well, you can think of these as being invariant under the maximal torus, because I haven't told you guys what the group L is in general. So, and finally, one last corollary, we have a Sego limit theorem, which is really a corollary of the main theorem and a theorem by these three authors from about 40 years ago. So I think I should leave it there. I apologize for giving such a light speed presentation at the end. Quejas, denuncias, as they say.
Any question? Yeah, Miguel?
The quantization with the use of Toeplitz operators, I mean, there's an advantage of that. There is something that you can do, or you can understand better with this perspective.
That's a good question, and this is where again I have to admit to not being a mathematical physicist, and other than to say that I mostly studied these for mathematical reasons, and then basically because I felt like I had to somehow justify my presence. I explained a little bit what the relationship with the physics is, but I actually do not know if there's some advantage for mathematical physics to considering these um, quantization methods. I do know that they're extremely famous, but I don't know what sort of things they have allowed people to do that were not possible by other methods.
Any other?
About, I'm not sure this is what is meant, but let me ask anyway. You had statements about the limit n to infinity in
yes.
the end, but is it also? I mean, would it also be related to the capital N in the beginning to be infinite? I mean, that you start with infinite dimensional spaces right away?
Yes, that is related because so there you are starting with finite dimensional spaces and you're letting the dimension go to infinity. So this is a very similar sort of thing. And what's a little bit different here is that the spaces that we're acting over are not contained in each other like nesting dolls, which is the case for the classical Sago limit theorem. These are sort of different spaces on different line bundles. It's just that they somehow are behaving more and more and more classically as n goes to infinity in some sense, which is made explicit by taking the Barrison transform of product of Toeplitz operators. Basically, so basically the Barrison transform as n goes to infinity becomes closer and closer to just an algebra homomorphism.
I mean, I think you know the book of Barry Simon and the Segal theorem. You know that he has a book.
I have to admit ignorance of that particular book by Barry Simon.
I see. I mean, in your version of the Segal theorem, there is something new that it's just a new perspective, or do you have something?
Well, it's so here I'll go to the references. It's mostly just sort of a corollary that came out as a consequence of the theorems that we ended up proving. So we ended up proving these results about the what do you call it, the approximate identity, these formulas for the Barrison transform, etc. And there's basically I don't remember how I was searching the literature and somehow I randomly came across this article, which has a very general Sago limit theorem. And it turns out that what we have, it does not technically fit the hypotheses that they have there, but bless you. But it turns out that what we have is enough for all the theorems that they have, for all the proofs that they have to work out. So it's basically, it's just that at the end of what we had proven, we realized, oh, well, then as a corollary, you get this result also, because then we have all the hypotheses necessary for this previous result. So I can't say that we were motivated by the Sago limit theorems.